Good afternoon, everyone. My name is Puspa Gorai, student of 6th semester Geology Department, JK College, Purulia. Today, me and my friend Payal will discuss the topic fluid flow. Now, we will be discussing the topics which are given here. Let us start with fluids. So, what actually are fluids? Fluids are substances that change shape easily under their own weight. Air, water, and water containing various amount of suspended sediments are the fluids of interest in sediment transport. The basic physical properties of these fluids are density and viscosity. So, differences in these properties markedly affect the ability of fluids to erode and transport sediment. As you know, fluid density, commonly referred to as rho, is defined as mass per unit fluid volume. So, density particularly influences the movement of fluid downslope under the influence of gravity. It also affects the magnitude of forces that act within a fluid and on the bed, as well as the rate at which particles fall or settle through a fluid. So it is slower in denser fluid and vice versa. As density varies with different fluids, so this density difference influences the relative ability of water and air to transport sediment. For example, water can transport sediment of much larger size than those transported by wind. After density, we now come to another important factor that influences fluid flow, that is fluid viscosity. It is a measure of the ability of fluids to flow. Put simply, fluids with low viscosity flow readily and fluids with high viscosity flow sluggishly. For example, water has low viscosity than honey. Now, we will see what is molecular viscosity. Molecular viscosity is the measure of resistance of a substance to change in shape taking place at finite speed during flow. It is the proportionality factor that links shear stress to the rate of strain, defined as the ratio of shear stress to the rate of deformation sustained across the fluid. It is expressed as mu is equal to tau divided by du by dy, where mu is the molecular viscosity, tau is the shear stress, and du by dy is the rate of deformation. For a more rigorous examination of viscosity, we consider a simple experiment. Here in this illustration, a fluid is enclosed between two rigid plates A and B. The fluid can be thought of as forming parallel sheets between the plates. A shear stress, which is tau, acting parallel to the plate, creates a steady state velocity profile, which is shown by the inclined lines, where fluid velocity u is proportional to the length of the arrows. The shear stress may be thought of as the force that produces a change in velocity relative to height, as one fluid layer slides over another. Thus, the ratio of shear stress to the rate of deformation is the molecular viscosity. Now, both density and viscosity increases with decreasing temperature of the fluid. So increasing viscosity tend to suppress turbulence, and decreased turbulence also reduces the ability of running water to erode and transport sediment. As both density and viscosity strongly affect fluid behavior, so combining them we get kinematic viscosity nu, which is the ratio of molecular viscosity to density, and expressed as nu is equal to mu divided by rho, where nu is the kinematic viscosity, mu is the molecular viscosity, and rho is the fluid density. Fluids in motion display two modes of flow depending upon the flow velocity, fluid viscosity, and roughness of the bed over which flow takes place. These are laminar flow and turbulent flow. Now we can define laminar flow as the steady flow of liquid over a horizontal surface in the form of layers of different velocities. For example, flow of ice and mud flow are essentially laminar. On the other hand, the flow of liquid with velocity greater than its critical velocity is called turbulent flow. Most flow of water and air under natural conditions is turbulent. Let us see what is Reynolds number. In 1883, Sir Osborne Reynolds reported a classic series of experiments addressing the problems of how laminar flow changes to turbulent flow. The fundamental differences in laminar and turbulent flow arise from the ratio of inertial forces to viscous forces. Thus, the relationship of inertial forces to viscous forces can be shown mathematically by a dimensionless value called the Reynolds number, which is expressed as Re is equal to rho UL by mu, where Re is the Reynolds number, rho is the density of the fluid, U is the mean velocity of the flow, L is the water depth, and mu is the molecular viscosity of the fluid. If Reynolds number is less than or equals to 500, then it is considered as laminar flow, and if it is greater than 2000, the flow is usually turbulent. Now, let us come to bed roughness. As you know, obstacles on the boundary of the flow generate eddies that influences the turbulence. So more the obstacle, the more is the turbulence. Now, roughness is consist of two components. When the boundary is consist of loose movable grain, it is called grain roughness. On the other hand, bed form of another component into which sediment is molded, it is termed as form roughness. And when less relief of a flow restricts the generation of eddies, the bed is described as smooth. Now Payal will discuss the rest of the topic. Thank you.